Now you'll need basic, huh?
Portion of this.
One question.
According to
Yeah, okay.
coming there. It's coming there, Priya. Some nonsense is happening.
Okay.
Sound खुलना है camera. Yeah, so good morning, everyone. There was this just mess up with this thing. Yeah. So we will be looking at the statistical techniques for astronomy. Can you hear me, all of you? If you can hear me, I hope you all can hear me. I'll just proceed ahead now. So we'll be looking at statistics, which will be used for astronomy in the next few lectures. And there has been a changing perspective. There was a time when people thought that statistics was not a good idea to interpret data and things. Yeah? Like Ernest Rutherford said, if your experiment needs statistics, you ought to have done a better experiment. Albert Einstein said, God does not play dice with the universe, uh, trying to imply that things, it's not that you have to say probabilistic, you can deterministically say everything or anything. And if you are unable to say concretely with 100% guarantee, then there is something you are missing out on the parameters, things which affect that event. So there is nothing called probability that this may happen or that, but you can actually predict how things work. Then there's a very famous statement made by Benjamin Disraeli. He says, lies, damn lies, and statistics. And people very often say statistics doesn't lie, but liars use statistics, right? So it's very important for us to use statistics properly. And now we have come to the realization that in the present era of rich data sets, it is essential to have sophisticated statistical techniques and methodologies to analyze and interpret data. Statistics too has changed its meaning over centuries. Originally, it referred to collection and compilation of data. In the 19th century, it accrued the goal of mathematical interpretation of data. And the contemporary statistics is an amalgam of science, technology, and art. This is what the famous statistics genius, Professor C.R. Rao, says in his book, Statistics and Truth. Astronomy too has changed over the years. It has gone from data poor to data rich science. Earlier, people had naked eye observations, then they went into using telescopes, and what they saw is what they drew on the notepads. And then it has evolved in time. You had photographic plates, you could image not one star, but a cluster of stars, tens and twenties of them in one shot. And then the detectors have improved over the years. And in every frame, you can get hundreds and thousands of objects. We live in this era of big astronomical surveys. We have 2DF Galaxy Redshift Survey, which gives redshift survey conducted by the Anglo-Australian Observatory between 1997 to 2002. We have SDSS, the Sloan Digital Sky Survey. We have optical and spectroscopic surveys, which were done between 2000 and 2006. Deep 2 Redshift Survey, done by Keck telescopes to measure redshifts of 50,000 galaxies. SAGE Legacy Unified Globular and Galaxy Surveys. LAMOST Survey, Optical Gravitation Lensing Experiment. We have the TUMAS Survey, Gaia, and Gaia, which we shall be doing more in detail with Priya, is designed for astrometry. It gives very accurate positions and distances and motion of stars with extremely good precision for about 1 billion stars. So it has become essential for astronomers to handle the big data sets and interpret the complex astrophysical problems by using sophisticated statistical techniques and technology. It has become essential. We cannot proceed ahead. We cannot give out our results without a statistical backup, statistical tests. You can't publish your data if you don't have your statistical support to the inferences which you make. So we have these large data sets which we have been collecting over all these surveys. You make a selection from that, you get your target data, do some pre-processing. In many of these surveys, before they put it up on the archive, it is pre-processed data, and there are times when you have to pre-process it yourself. Then you make certain transformations to suit what your aims are, as to what you are looking at. And then you do the data mining, you pick up those aspects of that data which you are interested in. You interpret that, you see patterns in it, uh, doing statistical analysis, finding their mean, median, their measures of central tendencies, measures of variability, variation, and so on. We interpret, evaluate the data, and then you finally arrive to the knowledge, right? So it's a long process, and statistics these days is playing a very big role uh, in arriving at the true knowledge. So for completion, and for some people who had not joined in right when we began our journey on 1st of August, we have these virtual observatories. A virtual observatory is a collection of interoperating data archives and software tools, and it uses the internet backbone to disseminate this data. And this is given to the access is given worldwide to all astronomers, everyone who is interested, in a user-friendly manner. And there's an interoperability, right? We have seen this in various uh, lectures and demonstrations where you have Top Cat talking to Aladdin and Aladdin talking to Vizier, and there's an interoperability. And basically, you have data flowing in, and you have these tools, virtual observatory tools, to analyze it and make sense out of it. And there is, it's on a platform which is available to everyone. So the main goal is to make data accessible worldwide. Statistics, which is used in astronomy, the list is very large, but I have listed just a few things here. The probability theory, we have the time series analysis, ANOVA, correlation and regression, principal component analysis, clustering techniques. Then we have these hypothesis tests and point estimation for use of analysis of modern astronomical data, least square methods, maximum likelihood and Bayesian approaches to statistical inferences, resampling method and bootstrapping, goodness of it, and so on, right? So in the next few lectures, we will look into a few of these, not all, but some very specific ones which um, are important and which we have used when we have dealt with astronomical data, right? So probability is something which we know. We can look at it in a very simple way of flipping of coins, but then probability, when you look at it in a more deeper way, it becomes more and more interesting and deeper. So question one, if we flip an unbiased coin 3 times and all the 3 times we get heads, what would you expect in the next flip? And probably many of you would say that since it's an unbiased coin, and if we repeat this and you are getting, say, heads all the time, then the probability of getting tails should be high. So you would expect that a tail should come, otherwise you would start doubting the coin. But when the a priori information is it's an unbiased coin, right? So this very often happens. You flip a coin and you get a head, you flip it again, you get a head. And when you say what is the probability of getting a head or a tail, it is half. So what we basically mean is if you do it many times, you do it 100 times and 1,000 times. Suppose you do the 1,000 times, and somewhere around 500 times or 490, 480 times you'll get heads, and the remaining times you get tails. Obviously ignoring the fact that the coin can go and stand on its edge too. Yeah, we are taking heads or tail, two sides to it. The question too, yeah, so in the upper case, if something happens too many times, then you expect something else should happen the next time. Otherwise, there's some uh, goofiness going on in that. Question two, you have a picture on the left, which is a picture from our university, Mano. This is called the 4-chamber heart rock. They are heart rock. So these rocks have balanced for about 2,500 million years. So the question is it safe to stand under them? Will they fall? They have stood for so much time. So tomorrow, if I go and stand under it, is there a likelihood that it should fall? So if you go with the argument on top, you would say it's dangerous. If they have not fallen for so many years, they can fall any moment now. But then, uh, if you look at it probability properly, and you will see that if it hasn't fallen for 250 million years, then the likelihood of it falling the next day is very low. So it is safe to stand there. Probability in astronomy. Yeah, there is a question. Before 1987, 4 naked eye supernovae have been recorded in 10 centuries. What before 1987 was the probability of supernova happening in the 20th century? And there can be 3 approaches, 3 answers. The first one, where you say probability is meaningless, they say supernovae are physical events, in principle can be accurately determined. They are not random events. So talking about probability is meaningless. The second approach is from the frequentist point of view, 4 out of 10. So the probability that supernova has happened before this is 4 in 10 in the next 10, in 10 years prior to that. So here the assumption is supernovae were equally likely to be reported in the past 10 centuries. Hence, the probability, the answer to this is 4 in 10. And the third approach is a priori argument, where again it's something similar to the first one. In principle, we might know the stellar mass function, the lifetime of a star is a function of mass, and star formation rates in a galaxy, and the detection efficiency. And further, if you want to make your predictions better, you take into account metallicity, obscuration due to dust clouds, etc., and you can exactly come to an answer which would not necessarily 4 in 10, but it will be a more uh, accurate answer based on the knowledge of how many supernovae can happen in a typical galaxy, and putting in more information in that, and not just calculating the probability on the basis of how many were by chance observed in a certain period of time. So now if we cite a supernova in 1987, yeah, it was the first approach would say one supernova does not affect another, we can't predict, right? So the question is, before 1987, in 10 years, there were 4, and now in 1987, we have seen one more. And does it change the probability of? So first approach says you can't predict because one more addition doesn't mean anything. In the second approach, you get the revised probability of 5 in 10. And the third approach will say we'll improve the models with fresh data. Now we have new data, we have new details, we know what kind of a star exploded, and we know the metallicity of this one, and we can calculate metallicity of many more stars in the neighborhood, and right. So revisiting the supernova problem, when you are looking at it in a more statistical, the more modern way of handling probabilities, you look at it, you have data of 4 supernova in 10 centuries, and this rho is the probability of it happening in 10 years. So a priori on rho is uniform between 0 and 1, and we fit a suitable model. And model here is a binomial distribution where you have uh, 1, 0 or 1, right? Either you observe it or you don't observe it, right? So in the next lectures, I will look into these binomial distribution and Gaussian distribution in a very brief way to understand when they are applied. So a binomial is where you have a flip, 0 and 1. And then you have the posterior probability is probability of rho of given a conditional to the data which is given, and it is 10C4, and yeah, using the binomial distribution rho to the power of 4. The rho is the probability of it happening, and 1 minus rho is the probability of not have it happening, and 1 minus rho to the power of 6 into priori or on rho. And you normalize it between 0 to 1 to as 1, the integral of that, and substituting this value in this, you do the mathematics of it. You get these gamma 10, gamma 4, gamma 14, and you get this value. So you substitute it into this expression here, and you get the values for what you do. And then you say what is the probability. You get the curve which you are getting is thus, and you say the probability of what is the probability, what are the chances of it lying between a certain range in this. Yeah, what are the chances of that event happening. So you talk in terms of these curves. Another interesting and important analysis, the principal component analysis. Yeah, before that, I should also say that you have these measures of central tendency. You have mean, median, mode, where you find the average, which is adding up all the values, dividing it with the number of things, you get mean. Median is the middlemost observation, and mode is the most frequently occurring things. Then you have the measures of variability, where you say how much do they deviate from the mean, standard deviation, and quartile deviations, and so on, which shows how good are these measures of tendency which you have found, and so on. Then you have correlations and regressions, where you try to find if you have more than one uh, a variable. Suppose I have height of a basketballer and the performance number of uh, baskets he has scored over a certain period, and you want to find out whether there's a relation between the height and the performance. You try to find relations between them, right? So so you have correlations and regressions, and we shall do this in detail further. Uh, Having spoken, we have this principal component analysis, PCA, which is very often used. And what is PCA? PCA is the best correlation searcher. Suppose you have a sample of n objects and there are n parameters measured for them. PCA is used to find what is correlated with what, which variable produces prime correlation, which produces the second correlation, and so on, right? So when you have data, you have numbers and figures. You just staring at the data is not sufficient, but you have to make sense out of it. And you do it by using all these techniques. And very briefly, the task of PCA, we shall go into this in a more detailed way further down. The task of PCA is given a sample of n objects with these n measured variables, right? You have n rows and you have n columns. The columns keeps the different variables. Small n is the columns. And for each, we find a new set of uh, variables, sigma n's, that are orthogonal. So each one is a linear combination of the original variables with values of these coefficients such that their smallest number of new variables account for the much variance as possible. So you try to find out which are the, so you reduce the dimension of the data. You try to reduce the number of variables to a smaller set, and you try to see that which are the essential ones which are actually contributing to the phenomena, right? So if the performance of a person in an exam is, we are looking at, uh, you may have a lot of parameters on that individual, uh, the age of the person, the education background, the knowledge of mathematics, knowledge of physics, of biology, of his height and weight and color of the hair and so on and so forth. And you are trying to find out what is the performance depending on. Obviously, when you do a PCA analysis, you will see that the color of hair wouldn't matter whether the person is a blonde or a black or a brown or a, and so you'll leave out certain things, and you just find out to pull out from that those essential parameters which are uh, giving the most, the correlations, yeah, which gives you, so the primary and the secondary and so on. So we shall look into this in more detail as we go on. And as you see earlier, this earlier inferences were made in a very bold and in a very rough manner, and people were very lucky to have got the results they did. And today, if you try to do that without a statistical backup, you cannot get your theories or your observations accepted. For example, you have uh, this scatter plot of Hubble, where you have the distances on the x-axis and the velocity of recession which he got on the y-axis, and you have these data points here. It was a very, very bold thing to fit a straight line and get the Hubble's law that uh, the velocity of recession of galaxies depends on the distance, right? There is a lot of scatter. If I put a straight line today and without giving the statistics of the thing and say how much is the deviation from that, then people will not accept it. They'll say this straight line here is not good enough, right? So we normalize by subtracting them. Yeah, so when we do it today, we do it in a more mathematical, in a more rigorous way. We subtract the mean, we find the means of the velocities. You subtract the means from uh, the actual ones, and then you divide it by the standard deviation, right? And similarly, you do that for distances, and you try to fix up and you try to find the principal component ones and do it. Okay, so another quick illustration. Here we have, say, many clusters Yeah, you have 1, 2, 3, 4, 5, about 13 of these 11 things. The two more are cut out. So you have many open clusters. We have all these parameters. Yeah. So yeah, in this case, we have the capital N is these 10 which is being shown, and the small n are all these r radius of the core. Then you have uh, this masses. These are apparent uh, apparent magnitudes, and you have all these values, chi values, r limiting where radius of the limiting for the cluster, what is the limiting radius, and all these values. And if you stare at this data, you cannot make out any sense. You further have ages, we have masses of these clusters and various things. So we have membership, we have reddening, we have distance, ages, you have the initial mass function, we have the luminosity function, so many parameters there. And the best thing which you can do is first you do some kind of plots. You try to plot it, and that gives you some understanding of the data. So when you are doing statistical analysis, handling large data, one good way is to the plots, right? Plot histograms. And what you see on the left side is the distribution of galactic, these clusters, open clusters in longitude. And then you see that they are peaking at certain points. There are certain locations where you peak, in certain locations you see them less. And it starts showing a pattern that you have. Yeah, so it's exhibiting maximum in the region of active star formations near uh, uh, longitude 125 near the Cassiopeia, and also at 205. Yeah, and then you look at these locations at also again at 240 and 285. Yeah, so these are Canis Major, Cassiopeia, Monoceros, Katrina regions, and you see a pattern, and you see that okay, these are star forming regions. This is where you can see more clusters, galactic clusters. Then on the right hand side, you have distribution of clusters with ages, and you see that there is a peak around 7.1, yeah, and also around 8, right? So you see a broad maximum center at log t at 8 and a narrow peak at log 7.1, right? So with this, you can get some idea what is happening, what are the spread of the ages, and so on and so forth. Then you can do some more. We'll get into this data set in detail, but roughly speaking, you can do things like distribution of uh, absolute error distances. You can look at the age distributions, and then you can look at the distance from the center, and you can plot the color E B minus V minus E B minus V of this, and see how the data spreads, whether it's a Gaussian distribution, where are the peaks coming, and then try to understand what basically is happening. And then we can see whether there is you can see more younger clusters in the galactic plane or of the plane towards the galactic center or away. Yeah, whether there is a distribution with respect to the long galactic longitude, galactic latitude, and and try to understand the physics of the whole thing, and try to understand if something is happening, why is it happening, and so on. Right, and when we do that, we have to give all kinds of, you have to start statistically support, you have to give figures and values and say at how many of them are lying within a certain range or so. Yeah, what percentage and at what level of significance are you claiming what you are saying? If you are saying that the clusters which are towards the galactic center are usually uh, more compact ones, while you look at clusters which are far from the galactic center, they are more extended. Then if you are saying on basis of how many clusters you have observed, the numbers are sufficient to make an inference of that. And if it is showing that, then you try to explain why is it happening. So if you really see that the clusters which are away from the galactic center are larger than the clusters which are towards the galactic center, then you can probably try to understand in terms of the tidal stripping due to the, the more mass lying at the galactic center, right? So you have a cluster which is far from the galactic center, then the tidal force of from the galactic center is weaker there, so the cluster can hold stars to a larger extent. While the ones which are closer to the galactic center, the tidal forces are large, so the outer envelopes get diffused, and only the ones which are towards the core they would survive, right? So you'll have to see these patterns, speak about it in a statistical way, whether these results are significant or not, and make inferences. So look for relations between parameters, and then you try to see clustering and this thing, right? So here for the data set which we have used R to find these pairwise plots, and you can correlate various parameters against others. So you will see a symmetry on this along the leading diagonal. It's because it's the same thing being reflected, and then you will start seeing uh, uh, patterns appearing and so on. Okay, so similarly, relations between age and size, whether younger clusters are they have a bigger radius and the older clusters are smaller in size or vice versa, right? So yeah, you have ages less than 15 million years, you have ages between 15 and 150 million years, and between 150 to 1800 and greater than 1000, 1500, greater than 1000. And then you plot in, the diameter in parsecs, and you try to see what is happening, and right. And the first one shows that the median cluster diameter grows with increasing age. From the second one, you can see the compact clusters are rarer among very old clusters with ages between 1.5 gigayears. And finally, the third one shows that the youngest objects with ages less than 15 million years are probably a mixture of compact bound clusters and diffuse expanding associations and so on. So, right. So, looking at it, you have to see and understand. Uh, do some multiparametric analysis, looking at the internal structure, core and limiting radius, stellar evolution, extrapolate to the masses and do it. And look at the dynamical evolution, core and overall mass density, and mass function slopes. Look at how these slopes are. So we shall be seeing in detail. And like I said, staring at this data is not sufficient, but it makes sense only when you uh, you graphically interpret, look at it, and you do some statistical analysis of it, right? And and so on. Okay, so the tools, I'll run through the tools very fast. We have various tools. We have this SPSS package, uh, statistical package. It's a proprietary software. You'll have to buy it, but from internet you can download and use it for I think 20 days, which is free. But after 20 days you can't reinstall it on the same machine. You have to move on to some other machine to do that. You have R which is a open source software, very powerful, very good, freely downloadable, freely you can distribute it and do it. So we shall also see this R. I would not do SPSS because I have not, I don't have that software with me. But we can see R, give us very short introduction to R, which you can build over that. Then we have the virtual observatory tools, which we have discussed earlier, and we have Python. In VO tools, we have the tables, we have VO plot, Topcat, Aladdin, ESA Sky, VO spec, spec views, right? We have Aladdin and Sky. We have done these in detail, but just to remind to you, all these tools are there which can be used. For plotting, we have Topcat, we have VO plot, we have VO mega plot, we have stills, and VO converter, which converts from ASCII to VO tables formats, from fits to VO tables, and so on and so forth. And yes, we can use Python, again, a very powerful programming long language. You can download. We have had sessions on this, and we can have some sessions on this pandas and pandas profiling, where just with just a few lines of code, you can say data. You read data into a file, and you say data describe, and it gives you the mean, standard deviation, the minimum of it, the max of this, the quartile, 25%, 50, and so on, right? And you do the profiling reports, and it does all kinds of histograms between log, all the parameters which are there, and it gives you correlations, Pearson's, Spearman's, various things in just in a simple way. So we shall be looking at this in more detail. What are these statistical tests? When are they applied? Which tests are good when your data sets are small, and which tests are best for large data sets? And yeah, so with this, I will stop for today. Thank you. So if there are any questions, uh, any questions, then you can put it up on chat, or we can discuss. Maybe this was okay. So next Saturday and Sunday, chi values. Yeah. So significance. Yeah, significance of chi. See, chi-square, we'll be, Subhashish, we'll be looking at these ones carefully. We try to find the squares of the deviations, and you reduce the deviations to the minimum. So the chi-square deviations which we do, it try to find fits. So you have a data set, and you try to fit a certain curve to that, and you try to fit such that what you get from this uh, expect, theoretical values which you get, and from actual ones, you try to minimize that. You try to, the deviations from, uh, suppose we have a data and you plot it and it looks like a straight line. So you try to fit a straight line to that, and you try to take the deviations from this line, squares of the deviations, and you minimize it. That's a technique. And then you find which is the best line to that. Similarly, if the data shows some kind of quadratic or biquadratic, then you fit those. And so chi-square tests are used for that. So some very specific ones which are very important, which are very frequently used, is what we shall deal into it. Priyam asked, can we have sessions on R? Yes, we'll have some sessions on R. I have used R extensively earlier, but over a certain period I have not used much. But yes, we will go into R and we'll look into it, and we'll give you a kickstart so that you can uh, build on what we start off with, right? So we'll have some sessions on R. Okay, yeah. So if they are, yeah, so we have come to the end of the session, and if there are no more comments or questions, then we'll stop for today. Thank you all, and bye bye till we meet next week.